If you've listened to Brewlosophy at all, you know how much we love Imperial Yeast. The company was founded on the ideal that if you're going to do something, do it right. From their Imperial Pitch-Right pouches, packing a whopping 200 billion cells of healthy and viable yeast in each pouch, to their commitment to commercial customers, guaranteeing 10 of their most popular strains are in stock for orders up to 20 liters, or the shipping is free, Imperial Yeast does it right. No more worrying about whether you need to make a starter or propagate your yeast prior to pitching. Imperial Yeast makes it easy for the home brewer and commercial brewer to obtain direct pitches at proper rates when you need it. To place a commercial order or to get more information about everything that Imperial Yeast has to offer, head on over to imperialyeast.com. Welcome to the Brew Lab. One of the main reasons that we add hops to wort and boil them is to add bitterness. Alpha acids in hops change their structure to become very bitter, but it's not a one-to-one conversion. In fact, there's a lot of loss. Brewers are often lucky to get 30 to 40% of the alpha acids to convert into bitter isos. So where does it all go? Could we be more efficient with bitter acid utilization? I'm your host, Cade, and today in the lab I'm speaking with Ph.D. candidate Mariana Barreto Carvalhal Pinto from the Universidade Estadual de Campinas in Sao Paulo, Brazil. And now bitter acids have been studied in beer for decades, and it's sort of been assumed that we're just going to get the conversion that we get. We don't actually need to add a lot of hops to add a lot of bitterness to beer. So brewers have largely been happy with the trade-off. But should we be happy with the trade-off? Could we be more efficient if we knew where the hop acids are going, why we're losing them? And if we can answer those two questions, can we control it? Can we start increasing utilization if we knew what interactions were occurring and where these bitter acids are going? Now, finding something new in an area that's been well researched is difficult, and it takes a new perspective, which Mariana is able to do by looking at hop protein interactions. Those same interactions that make foam and haze could also be why we lose so many bitter acids during the boil. By looking at the protein content of wort made with and without hops, we can learn where bitter acids are going and how we might be able to change it. So this whole concept of proteomics, or looking at how proteins in beer might change, is where we laid the groundwork last week with Dr. Glenn Fox, and where we'll spend some time over the next few weeks looking at the brewing process in a new way. So I hope you enjoy it, and especially in this one, looking at how bitter acids change during the boil. All right, we're about to wrap up 2023, and as we look at the year that's passed, I'm incredibly thankful for all of you, our listeners, and especially for our patrons. We wouldn't be able to do this thing without any of you. If you're not currently a patron, I encourage you to head over to patreon.com/brewlosophy and check it out. By becoming a patron, not only do you get to help us keep going, you also get to have access to Brewlosophy contributor recipes that we've never published, new discounts each month at YakimaValleyHops.com, and for $3, access to a monthly live Q&A session with a special guest from the brewing industry. Now, we've had guests like John Palmer, Jamil Zainashev, Vinny Chilurzo, and even Mr. Brewlosopher himself, Marshall Schott. So when you sign up, all of these prior sessions become available to you on our private Patreon Facebook page, as well as a new guest each month. So please head on over to patreon.com/brewlosophy to find all the information to get access to this awesome resource. Thank you to everyone that's left a rating or review of the show. If you haven't yet left a rating or review, please do so. I love hearing from y'all. It's a great source of feedback, and it helps others like you find the show. So without those reviews, we wouldn't have the Applying the Science series with Jordan, and the show wouldn't be what it is today. So thank you to everyone that left a review this year. And if you haven't yet, please take a moment to help me out. Feedback is brought to you by the folks from John I. Haas, who over the last couple years have released a handful of really cool hop products like Lupamax, Incognito, and Flex, all intended to improve beer while reducing vegetal matter and thus increasing yields. Well, they're excited to announce their latest 100% hop-derived product, especially made for your patio, lawnmower, or beach beers. Kettle Ready imparts smooth, light, stable bitterness and kettle hop aroma to beer while offering microbiological protection during the brewing process. This new product is easy to use and has no special dosing requirements. Plus, due to its standardized high alpha acid concentration in a light, stable molecule, it gives the light stability and bitterness characteristics desired for all traditional beers. And it plays well with other Haas products, including Tetra Hop Gold, Hexa Hop Gold, and Ready Hop, for flexibility and optionality when brewing light, stable beers. Learn more about Kettle Ready at johnihaas.com. That's John, the letter I, Haas.com. All right, listener Jordan wrote in about episode 136, Free Amino Nitrogen with Dr. Glenn Fox. He said, "Hi, Cade. I just listened to the latest episode talking about fan in the brewing process. My question for you is, how could I go about testing fan levels in finished beer? Is that something that can be done with typical brewery lab equipment, or does it need to be sent off to another lab? It may have already been mentioned in the podcast, but I may have missed that part. I work at a commercial brewery as a lab tech, cellar person, and assistant brewer, and I'm looking for ways to improve shelf stability in finished beer, and analyzing fan levels throughout the brewing process is something that I'm interested in. Keep up the great work. I love listening to the Brew Lab and Brewlosophy podcasts on my commute to work." Hey, Jonathan, thanks for the great question. Yeah, there is an ASBC method, WERT 12. So it's WERT 12 ASBC method that provides instructions for measuring fan using ninhydrin and a spectrophotometer. You might have a spectrophotometer already in your brewery. If you don't, it's fairly inexpensive. Basic spectrophotometer and also ninhydrin, also fairly inexpensive. But if you don't have those pieces of equipment, then yeah, you won't be able to do that in your brewery. Also, another note about that method, I have heard that the method is somewhat difficult. Not impossible, but it's kind of above average difficulty. So depending on your level of lab skills and your comfort with that, you may or may not want to do that method yourself. Now, of course, depending on the number of samples you're going to send off or you're looking to test, I might recommend sending them off. I mean, Glenn mentioned reaching out to your local university to check to see if they do the analysis. And of course, sending it into Cal Davis or OSU or one of the other universities with a brewing program. They could probably do that analysis for you. Now, of course, there might be a fee for service that you might have to pay for. And I have no idea what the cost is at any of those institutions, but you can definitely reach out to them and see, so that might be a way to do it. And depending on the number of samples, especially if it's a local university, they might be able to help you out, especially if you bring some beer over. I know scientists love beer. So if you have any questions about the analysis or you run into any troubles, just shoot me an email and I'll help you where I can. I haven't done the analysis myself, so I'm not an expert on it, but I do have a colleague that did it as part of his Ph.D. project. So I'm sure we can help you out there, at least point you in the right direction. And again, check out WERT 12, the ASBC method. All right, I'm going to take a quick break and I'll be back in a few minutes with Mariana Barreto Carvalhal Pinto talking about what happens to hop bitter acids during the boil. The dry yeast revolution is here, and Cellar Science is leading the charge. Cellar Science has expanded the world of dry yeast far beyond the drab landscape of yesteryear. With over 20 strains of beer and wine yeast now available, you can brew any style. Not to mention that their unique growth and harvesting process greatly increases lipid levels in yeast cell walls, removing the need to aerate your wort on the first pitch and allowing you to directly pitch without rehydration. Couple that with the other advantages of dry yeast, such as higher cell count and viability, and you can clearly see why commercial breweries across the U.S. are using dry yeast and choosing Cellar Science.
Looking for a fun way to win up to 25 times your money this basketball season? Test your skills on Prize Picks, the most exciting way to play daily fantasy sports. Just select 2 or more players, pick more or less on their projected stats, and place your entry. You could turn $10 into $250. Right now, Prize Picks will match your first deposit up to $100. Just visit prizepicks.com/fan and use code FAN. That's code FAN at prizepicks.com/fan.
Must be present in certain states. Visit prizepicks.com for restrictions and details.
One of the core components of the brewing process is boiling the sweet wort post-mashing to concentrate the wort, create color, remove DMS, and coagulate proteins, along with isomerizing hop acids into bittering compounds. And my guest in the lab today to talk about what happens during the boil is Ph.D. candidate Mariana Barreto Carvalhal Pinto of the Universidade Estadual de Campinas in Sao Paulo, Brazil, as well as from the Technical University of Berlin in Germany. Mariana, welcome to the Brew Lab.
Wow, thank you very much, Cade.
I'm glad to have you here. And in Germany, which is famous for its lagers, hops are prized for their bitterness. Although I hear there are increasingly more IPAs available. Is Pilsner still the king or queen in Brazil, or are there more popular styles?
Well, in Brazil, we can categorize into 2 beer sectors. One is the mainstream, which is composed by the light lagers, and it fits pretty well in the Brazilian hot summer.
Yeah, totally.
But it's been rising lately, craft scene in the past decades, which is pretty similar to the US, with more hoppy beers. So we consume a lot of IPAs, New England IPAs, and also the style to brew is close to the US. Pretty crazy with a lot of hops.
Crazy with a lot of hops. Yeah, I certainly can see that. It seems like Germany is the one that's holding out. Although again, I do hear that there are more IPAs becoming available there. Yeah, it's the same in the United States too, right? Mainstream beer, the Pilsner is the king, the light lager is the king. Yeah, so same here. Interesting to hear that in Brazil, and for the same reasons, I think for a lot of the country, it's really hot during the summer. So those light lagers are very quenchable. Well, and anyway, we're going to talk today about some of the work that you've been doing for your Ph.D. And you are, as I understand, a Ph.D. candidate at both the Universidade Estadual de Campinas as well as the Technical University in Berlin, studying there with Dr. Brian Gibson and Dr. Philip Wheatstock at TU Berlin. How did you become interested in studying brewing science?
Well, to answer this question, I have to head back to 2011.
Wow, okay. Yeah.
When I was already doing my bachelor in food engineering. But then I started to consume more and more beer, and I could see that there were a lot of different beers with different sensory profiles. And I got interested on that, how it's made and so on. And then I started to home brew. And together with my my bachelor studies, I started to study more about brewing science and dig into that field until my master, which I studied about hops. And then this led me to PhD, and I never stopped it.
And you never stopped. That was fun too. So your master's was done also in Sao Paulo, right?
Exactly. I've done my master's studies in the same university, Universidade Estadual de Campinas, and my bachelor as well.
Yeah. Great. And very, very cool. And as I understand, you're going to get a diploma from both TU Berlin, Technical University of Berlin, and the Universidade Estadual de Campinas.
Exactly. I am the way of getting the diploma in both universities. I am already enrolled in both, doing my PhD. And then, next year we will see. Hopefully, I will defend my thesis and get those diplomas.
Yeah, wow. Well, hopefully, good luck to you, and congratulations there. So for being close to finishing. So yeah, you've done some research, and in discussing this before the show, you looked at making hop extracts with Brazilian hops, which is something that I think will be very interesting, and hopefully have you on for another show in the future. But the topic of this episode is work that you've done looking at what happens to hop acids during the boil, and taking a little bit of a different perspective, right? I mean, I think a lot of people have spent time looking at hop acids, and understanding that, they change, they isomerize during the boil, and we'll talk about those sorts of reactions that happen. But there's also an interaction of hop acids and proteins in the boil, and that's kind of been your area of focus. So we'll talk about that and talk about why that might be important for brewers, and then talk about an experiment where you analyzed what happens to the proteins in the boil due to exposure to hops. Does that sound like a plan?
Yeah, we actually have some future work going on. One, hopefully we will publish soon. It's about the barley variety difference and the influence in the hop utilization.
Oh, okay.
So yeah, seems that depends on the barley malt and barley variety. The utilization of hops during the wort boiling could be higher or not.
Ah, interesting.
Yeah. And then I'm going to perform some proteomic analysis on that as well to see which proteins also might play a role in that.
Yeah, which proteins might play a role. That's really interesting. This whole concept of proteins is something I've been fascinated with recently. There's been a number of episodes on proteins. Like we talked with Dr. Glenn Fox about FAN, and just a number of things that have come up with where we need to look more at proteins and what's going on in the boil and throughout the brewing process. So we should start there, and I want to start kind of with that very open-ended question: is what happens during the boil?
Yeah, during the boil happens a lot of things. So just point out because the boil is one of the most important steps during the brewing process. Without boil, the beer wouldn't be bitter because we need the boil to isomerize the alpha acids, which already talked about. But also to volatilize some of flavors like the MS, clarify the wort through the protein precipitation. So the protein is not that bad.
Yeah.
And also concentrate the wort, Maillard reaction to give color in beer and so on.
Yeah, just quite a lot of things, right? I mean, we often think about like, oh yeah, the boil is just, to get bitterness in through the hops, but that's one piece of it. There's just so much else that's going on, right? Evaporation, concentration, precipitation of proteins, protein denaturation, and some of those things are very good for the beer, right? We have proteins being denatured that provide fuel for yeast during fermentation. We have proteins that contribute to haze, or reduce haze that actually clarify the beer whenever those proteins fall out. So there's quite a bit of things that are happening during the boil. It's not just hop bitterness. But I wanted to talk to a little bit about that because your research is sort of focused on what happens to proteins in the presence of hops and not hops. So how do hops contribute beer bitterness? How does that work?
Well, nowadays the brewers talk a lot about hops because of its aroma profile and the IPAs, but hops also is known as the beer's gold because hop contains some unique compounds that can give bitterness in beer, and this name is alpha acid and alpha acid isomerize. This is one chemical reaction during the wort boil, and therefore needs the hot high temperatures, and transforms in those compounds called isoalpha acids.
Yeah. So hop alpha acids get transformed to isoalpha acids, which are super bitter, right? Isoalpha acids are way more bitter than regular alpha acids, beta acids, and other hop bittering acids. So that is a key component of the boil, right? That's a key part of the brewing process is adding hops in there to get that bitterness to offset that sweet wort or sweet alcohol that's left in the beer at the end. Now, you mentioned already that you're doing some future work in hop utilization. I think we could talk about this project today as an exercise in hop utilization a little bit too, because one of the questions and one of the things that was interesting from your paper is, what happens to hop acids during the boil? Is there a 1-to-1 conversion from alpha acids to isoalpha acids? Or stated differently, do all of the alpha acids convert 100% to those bittering isoalpha acid compounds during the boil?
Well, by the chemical reaction, theoretically, yes, it should, but the reality is totally different because there are a lot of parameters playing a role during the wort boiling, and wort is a really complex matrix. So most of the isoalpha acids or the alpha acids will be lost during this process. By the literature, it's around 50%. And also by the brewery's experience as well. And because those compounds are not that soluble. So alpha acid needs first to solubilize in the wort to be converted into isoalpha acids. So due to this low solubility, most of the alpha acids will be lost also to the troop. And Maybe also because of the proteins.
Yeah, maybe also because of the proteins. And that's where your research has come into this, right? I mean, I think most brewers are aware, they've seen this, right? That you put in beers and if you can't assume 100% utilization, right? I think a lot of places are looking at like 40% or lower in terms of the amount of bitterness that you'll actually get or the amount of iso alpha acids that you'll get from using alpha acids in a beer. And so that's one of the questions, right, that you're trying to answer. And I'll ask it to you in this way. Where is the loss? Where are these hop acids going during the boil?
Well, they go to the troop for sure, which is a waste during the boiling process. And normally after the ripple, the troop will be removed from the process. And then those compounds will be there together with a lot of protein, polyphenols, and some other minor compounds.
Yeah, and are there ways to decrease the amount of loss that goes to the to the trub, or stated differently again, increase the amount of bitterness that makes it into the wort?
Yeah, actually, what we already know, there are some parameters during the process that could be used to improve, such as pH. It's one of the main parameters for alpha acid solubility. So if we increase the pH during this process, this also could cause some side effects, but if we increase the pH, the solubility of alpha and isoalpha acids will increase. Also, the temperature, in higher temperature, the conversion is higher, and the density of the wort as well. With low density wort, higher is the conversion as well.
Oh, interesting. So a couple of different things there. Increasing pH might increase the amount of bitterness that makes it into the beer. Decreasing the wort density, so making it not as like thick, not as sugary, might increase bitterness. And then temperature, right? That you said like temperature plays a role as well. So keeping it boiling might actually increase that bitterness. So then why is there so much alpha acid that gets lost to the trub? Is it sticking to things and dropping out of solution? What's going on there?
Well, because the pH that it's normally in the wort right now, it's an acidic pH, so it's around between 5 to 5.5, depends on the process. But therefore, most of those compounds are lost because of the solubility, but also they might link binds to proteins in the protein aggregates. So those aggregates could then carry them out to the trub.
I see. And so then that's this. We need to talk then about proteins, right? Because it sounds like there may be some binding of proteins. And again, this is where your research has looked at what's happening to these proteins and the hop protein interactions. So what role do proteins play in beer quality? Why are proteins? Why do we care about proteins as brewers?
Yeah, protein is well known for two main reasons. For foam stability and haze stability. So both could be good or bad, depending on the beer style, actually. But then foam stability, we have some called foam active proteins, which is well known that stabilize the foam and gives that white with small bubbles foam in the beer, and the haziness as well, like some proteins such as gluten protein, which is a well-known protein that also plays a role in the haziness in the beer. So protein is, as I said, is not that bad. Could be.
Yeah.
good as well.
Yeah, it could be good. I mean, you need proteins for foam, right? And foam is something that we like in beer. It makes it nice and bubbly and effervescent. It increases flavor, all those things that we've talked about on prior episodes of the show. And if you're doing making hazy IPAs, making a stable haze is important, right? And so you need some protein there to create that protein polyphenol complex that I've talked about with Laura Burns. But then also, if you want haze to drop out, if you want clear beer, you need protein aggregate, right, to drop out of solution so that those things aren't causing haze in your beer. So, okay, so that's the role of proteins in beer. Now I want to talk about isoalpha acids and proteins, right? We know that, or at least we've talked about that isoalpha acids on prior episodes, we've talked about that isoalpha acids interact with proteins to improve foam quality. It's that interaction between isoalpha acids and protein that helps us have like a nice foam. Well, then why do so many alpha acids end up in the tube? Why do we lose so much that's in the tube? Why isn't that sticking in solution and staying around longer?
Well, in the same that isoalpha acids interact with the foam active protein, they also interact with the other wort proteins that we still don't know, because most of the research are made with the foam active proteins or the haze active proteins. So there are other minor proteins that doesn't play a role in the beer quality that also could interact with those isoalpha acids. So we have to think that that wort is a really complex matrix and comprise more than 200 proteins. So during the wort boiling, the protein form complex, as you said, protein complex, and this is the formation is facilitated by the polyphenol bindings, but also it's known that isoalpha acids could interact and help to form those aggregates, those complex. And these aggregates might encapsulate the isoalpha acids and keep them inside, carrying them to the tube.
Ah, interesting. So in the same way that polyphenols are interacting with proteins and creating these complexes, it's the same with isoalpha acids. They might be interacting with the different proteins and then dropping out of solution with the aggregate.
Yeah, exactly. We can compare it, of course, the chemical formula of polyphenols, and also there are hundreds of polyphenols. So it's but we can compare with the isoalpha acids the way how they interact with those proteins. Like they can interact with some specific amino acids, for example, cysteines, or with some enzymes, the active site of some enzymes as well. So yeah, probably though in the tube we have like a soup of everything, like binded together.
Yeah. And, this is something interesting, too. I mean, Glenn Fox brought this up, and I think John Pralmar also brought it up on a recent episode. And it's that we often talk about like proteins or fan as if it's this just total clump of things. But as you mentioned, that there are many different types of proteins, and there's many different types of free amino nitrogen. So just talking about it as a clump doesn't really paint the whole picture. So do isoalpha acids bind, preferentially to certain proteins over others, or are there certain proteins that isoalpha acids just don't interact with? Or do you know, or maybe that was one of the questions of your research?
Yeah, this question, being honest, is still open because we would like to investigate in depth which proteins really the isoalpha acid binds. But from our study, what we could see is that there is an indicative that isoalpha acids might bind to some proteins instead of others. For example, enzymes, as I said, because enzymes has the active sites, and these sites inside the protein normally forms hydrophobic bonds. I'm sorry, talking more chemically, but
that's okay.
and then these hydrophobic interactions, we know that could happen with iso-alpha acids. And also, there are some metals in the active sites as well, such as calcium or iron. And iso-alpha acids is also prone to react with those metals.
Specific proteins. So some of the proteins are sort of better suited to bind with alpha acids. I mean, that makes a lot of sense. There's a lot of compounds out there in nature that have preferential bonding, right? That some things like to bond with other things better. And so that makes sense that iso-alpha acid would have certain proteins that it bonds more with. So if we were looking at just looking at either just the total picture of the iso-alpha acids, like we're putting in this amount of iso-alpha acids and we're only getting out, let's say 40 or 50%. That's one way to look at the picture. And then if we're looking at like how much trube formation is formed, then we see a lot of trube that's formed and there's probably iso-alpha acids in that trube. That's also one part of the picture. But the interaction between iso-alpha acids and proteins could also be important too, right? If we know which proteins are binding with hop bitter acids, then we know, I guess what? I'd ask you that question. If we know which proteins are binding with hop bitter acids, what do we know about the boil that we didn't know before?
Well, this opens a totally new world, actually, because, as I said, protein is really complex and there are a lot of proteins, but we could then track down into the barley variety, which is also a following up study, to deplete those proteins, and which might play a role in the hop utilization, but not in the beer quality, for example, or decrease the amount of those proteins during the malting process. We don't know, but we could then offer alternatives to decrease the amount of those proteins or increase others.
So like potentially breeding new barley varieties to help hop utilization.
Yeah, exactly.
Interesting. That's really cool. That does kind of open a whole new world. If once we start to see which proteins bind to hops, we start to know, okay, let's decrease that protein. And then we don't have those proteins that are binding to hops, which means more bitterness in the boil. And that's efficiencies for the brewer, less hops that they have to use in the boil, and a whole new world. Wow, that's pretty cool. Yeah, pretty cool research. All right, well, let's talk then about your study design, and then we'll hit the break before we get back to the results. So why don't you tell us what you did in your study to look at this like protein hop interaction?
Yeah, so the goal here was to see if the hop addition would play a role in the formation of the aggregates or the protein profile during the wort boiling. So for that, we prepared one standard wort, and this sweet wort was split into two portions. One was added hops and the other not. So we had a sampling in the sweet wort and also in both in the hopped and unhopped wort, and we compared all those. Also, we analyzed other parameters for beer quality, normally like total nitrogen, FAN, polyphenols, beta-glucan, and of course, hop bitter acids in the hopped wort.
Mm-hmm. Yeah, bitter acids. And then, of course, the biggest thing of this, too, is looking at that protein analysis to see how the proteins actually came out in the wort that was hopped versus unhopped.
Yeah, exactly. And for that, we performed proteomic analysis and in the LC, MS, and we got a bunch of data to work with, but we could then I look at better in details on those proteins.
Yeah, very cool. Yeah, to look at the breakdown of the protein, which ones are actually binding to the hops. And then, like you said, that could give us information about, which barley varieties we should use or any of those things to increase, increase bitterness utilization in the boil. All right, well, cool. Well, let's take a short break. And then when we come back, we'll talk about how isoalpha acids interacted with the proteins and trub and get into your results. One of the biggest improvements to my brewing practices was the upgrade to stainless steel, and Delta Brewing Systems offers some of the lowest prices on high-quality stainless gear, like the Firm Tank, which holds 8 gallons or 30 liters of wort, comes with a domed lid to reduce the chances of a messy blow-off, and it can hold up to 4 psi of pressure. Delta Brewing Systems also has their own line of brew kettles, as well as one of the lowest-priced all-in-one electric brew systems out there, and their prices are remarkably affordable. If you're in the market for legit stainless gear that won't break the bank, you've got to check out deltabrewingsystems.com. We all know that designing recipes is really fun, and doing it well is so much easier with good software. We at Brewlosophy recently made the switch to Brewfather, and honestly, y'all, we could not be happier. Brewfather utilizes the latest technology to bring you the most robust cloud-based recipe design software that can be accessed anywhere, on your phone, tablet, desktop, and even offline. It also works seamlessly with numerous third-party devices to make it easier to monitor every step of your brew. I know change can be difficult, but trust me when I say you need to go to brewfather.app today to try it out for yourself. That's brewfather.app. Without hops, beer would be a semi-sweet, bready, toasty, crackery beverage. Hops counteract that sweetness by adding bitterness and a wide range of pleasant aromas. And bitterness is the focus of this episode. And Mariana, we've been talking about how hops are, of course, added during the boil to increase bitterness, but not all of that bitterness makes it into the beer.
Yeah, exactly. Unfortunately, most of the bitterness doesn't go into the beer. So the aim of my study was to look into details on the protein side to try to uncover if this would play a role in the bitterness loss during the wort boiling. Yeah, to confirm if hops are binding to proteins and what role that plays during the wort boil. And we talked just before the break about that you, as part of this experiment, the idea was to determine how hops impact proteins during the boil. So you made a sweet wort stream, and then split it into 2 batches, a hopped version and an unhopped version. And I forgot to ask you before the break, which hops did you use for this hopped wort? Well, to avoid any effect of polyphenols, we used the hop extract with around 47% of alpha acids. Okay, yeah. So a straight hop extract. So not worrying about polyphenols or any of the other interactions that are there. So just an iso alpha acid extract in the hopped wort. Okay, so then you've got your unhopped wort, your hopped wort. Were you able to confirm an interaction between proteins and hops? Yeah, sure. We could see that really the hops really changed the protein profile of the wort. Okay, and then where did the bitterness compounds go? Did you confirm that there are actually a lot of bitterness compounds falling out into the trub? Yeah, actually, we didn't analyze the trub itself, but we presume that probably it is in the trub because there wasn't elsewhere during our experiments. And then most of the bitterness is definitely in the trub. Yeah. Most of the bitterness is falling out there. And again, this sort of confirms what we already kind of know as brewers, right? We know that utilization isn't 100%. And so it's going somewhere. It's not in the wort that's being transferred out of the boil. So it has to go somewhere, and it's there in the trub, most likely. So, okay. So those are, again, basic understandings that confirm that, yes, what we know is consistent in this case. But again, we're not
looking at this from necessarily a hop perspective, right? We're not looking at what happens to the hop bitter acids. Well, sort of. We're kind of trying to figure out what happens to the hop bitter acids, but we're not looking at utilization for hops. What we're looking at here is like what happens to the proteins, right? What happens to where is it going, and why is it? Which proteins is it preferentially binding to? And that is sort of a proteomics discussion. And one thing I realized, you mentioned pH in the previous segment, but we didn't really talk about it. But I feel like we do need to talk about pH and solubility. So what happens to water soluble proteins, and what does that mean, a water soluble protein?
Well, water-soluble protein means that we'll extract, because in barley there are several proteins, but we will extract only the ones that it's soluble into water, into a cold system. So in the wort, we will have only water-soluble proteins. Therefore, I talk only about them now. Because in barley there are several other proteins.
Yeah, that's from the mash, right? Like we're talking about during the mash. I mean, there's a whole bunch of proteins that are present in barley, but the only ones that actually make it into the boil are the ones that come out in the wort, right? So there's a lot of protein that's left in the spent grains or whatever's left from the mash. What we're talking about here are water soluble proteins that come out of the mash via the wort stream.
Yeah, exactly that. And talking about the pH, as you said, the protein solubility is totally linked with the pH.
Okay, it's linked with pH. And if I remember correctly, without getting too far into the chemical weeds, there's this thing called a protein isoelectric point. What is the isoelectric point, and why is it important?
Well, I must go a little bit deeper in the chemistry right now, but I promise that it won't be too bad.
Okay.
So by definition, the amino acid structure contains always an acidic carboxyl group and a basic amino group. And as we know, protein is composed by a chain of amino acids. So in that way, those groups will have charge depending on the pH. So below the isoelectric point of a certain protein, because each protein has one isoelectric point, and below this value, the protein will be positively charged. Above the isoelectric point, the protein will be negatively charged. What does it mean? While the protein is charged, it will happen some repulsive force. So the protein will be more difficult actually for the protein bind to each other as outside the isoelectric point. But in the isoelectric point, the protein has a neutral charge, which facilitates, because there isn't this repulsion force, and facilitates the protein aggregation. And this, it's well known in the dairy products, because they use pH to produce some cheese or yogurt, but by achieving the isoelectric point.
I see. So that protein has at a neutral charge, the closer you are to that isoelectric point, the more protein is going to fall out of solution. So like in an acidic pH, proteins with an acidic isoelectric point will aggregate and drop out of solution. And beer is acidic. So proteins with those isoelectric points are going to drop out of solution. They're going to agglomerate and potentially bind with isoalpha acids and then drop out of solution. So are we seeing some proteins like hang around longer than others in wort?
Yeah, exactly. What happens during the wort boiling is that some proteins are more likely to precipitate than others. Especially by the isoelectric point. So the ones that has the acidic isoelectric points will precipitate more than the alkalinic one.
Oh, I see. Okay, yeah. So the ones that are sort of acidic, so alkalinic, isoelectric points are going to hang around. That means that we're retaining more of those alkaline proteins. So are there examples of alkaline, isoelectric point proteins, and do they have an impact on beer quality?
Yeah, sure. The main alkaline proteins are the LTP, which has a longer name called lipid transfer protein, but we call by the short one,
Yeah,
the nickname
LTP.
LTP.
Yeah.
And this protein is a foam active protein.
Okay. All right.
So it means that this protein plays a role on stabilizing the beer foam. And also another alkaline protein is the gluten protein, which is a haze active protein and plays a role in the haze formation during beer.
Oh, interesting. So a couple of those proteins we're very familiar with. Then we're very familiar with the protein that the LTP protein that increases haze, and then the other one, I think you said the gluten protein or glutamate protein, something like that that increases haze or promotes haze in beer. So it's interesting. So that's kind of one of the reasons why we have foam is because this chemical reaction and pH plays a role in that. Are there acidic proteins that drop? I guess actually, first of all, we need to know what proteins are dropping out of solution too, right? So we need to run your proteomic analysis of a hopped wort and an unhopped wort to see how hops are impacting the proteins that hang around in solution and the ones that don't. So another thing that you talked about in your paper, the way to understand this is there are what you're referring to as like molecular use proteins and biological process proteins. So what are those? And tell me about that distinction.
Proteins, they are involved in several roles in the metabolism of beings, like structural, metabolic reactions, DNA replication, and so on, so on. So protein therefore we have a lot of proteins because each family of protein has one molecular function, and it's called molecular function. So it is the specific function that the protein develops within a cell. So also inside the cells, like the cell wall, ribosomes, like RNA transcriptors. So there are a lot of enzymes and proteins playing a role in the molecular function of the being. And the biological process will look more wider in the protein functions. So it's the role that protein plays in the organism metabolism. So it could be, for example, like a plant defense protein, like a protein that plant produce to defend against fungus or bacteria attack or other microorganism attack.
Mm-hmm. Yeah. Okay. So that's again why proteins are used, like molecular use versus biological process proteins. All right. And then all right, back out of the chemistry and the biology weeds here. Let's take it back up to what we're looking at in the study. So then, are there specific categories of proteins that hang around more in hopped or unhopped wort?
Yeah, sure. What we could see in our samples that mainly proteins we found were plant defense, also involved in the lipid process. This is represented by the LTP protein, and storage proteins, which also is represented by the gluten protein. I know those I am talking a lot here, but they were the main proteins that we found.
Yeah, well, and those are interesting, right? I mean, that makes sense that those proteins are the ones that sort of hang around in solution. I mean, I think even in your paper, you said that the most abundant proteins were those that play a role in beer haze and foam formation, and specifically those hoarding storage proteins that are in barley kernels. So that's really interesting then that those proteins are hanging around in the wort, but there was a lot, I guess, dropping out of solution, right? I mean, there are a lot of proteins that were either dropping out or maybe what were present. So tell me, what else did you find in here? What other takeaways did you have from your proteomic analysis of the wort?
Well, the protein? It's the wort is a mix of protein, and then what we found that actually is not 100%. Like I am talking about some acidic isoelectric point that protein precipitates, but not 100% of those proteins will precipitate. For example, protein Z also plays a role in the foam formation, and part of this protein, some amount of this protein will still remain, despite it having acidic isoelectric point. So the isoelectric point is exactly the wort pH, but we can still find it afterwards. So not all will.
So not all of the acidic isoelectric point proteins will fall out. So there is still some protein that's in there. And so then are these proteins ones that are binding with bitter acids and causing bitter acids to drop out of solution? The ones like the acidic isoelectric proteins, is that where you see so much of this loss in isoalpha acids? Is this binding of proteins?
Yeah, what we could see also that the proteins that likely to interact with isoalpha acids are the one that doesn't play a role in the beer quality. So, for example, thionine, it's one plant defense protein that doesn't play a role on any of those quality traits, and is the one that was most significant on the difference between hopped and unhopped wort, as well as peroxidase. Peroxidase is an enzyme that also is a plant defense protein, and was the one that was really statistical different between the treatments between the hopped and unhopped wort.
Right. So the thionine and the peroxidase proteins were higher in unhopped wort than in hopped wort, which indicates that those proteins are binding with isoalpha acid or are binding with hop acids and then falling out of solution, causing loss of isoalpha acid.
Exactly. So probably those minor proteins are the ones that really interact during the formation of the aggregates, because when you think about the formation of the aggregates, it's not like fast. You can see it as during the wort boiling, the aggregates will get bigger. It's getting bigger. So this means that it starts like small and some layers start to bind. And in this process, those proteins might interact with the isoalpha acids or also alpha acids. We still don't know. And then encapsulate those compounds in those aggregates during the formation of the aggregates.
I see. So it's like a snowball effect, right? Like everything is snowballing and growing as you boil longer and for more time. Then everything is binding together and it's pulling those those hop bitter acids out of solution again. And you mentioned that like thionine and peroxidase, those aren't proteins that are known to impact beer quality. So, those proteins are falling out of solution, not necessarily impacting beer quality in the future. But this is, I guess, where you mentioned earlier, we might be able to look at barley varieties and find barley varieties that are lower in these sorts of proteins and then increase our hop utilization.
Yeah, exactly. And also thinking about like during the cultivation, because as those are plant defense proteins, the plant needs to produce those proteins when there are some infection, like as I said, by some microorganisms. So if uh, the farmers has more bigger problem in their plantation, they will have also more amount of those proteins. So this could also be depleted somehow by the process as well, as I said, by the malting. Like we still don't know, but this is still an open question.
Yeah, a lot of ways that we might be able to impact the protein content, right? Or not necessarily the total protein content, but the breakdown, the specific proteins that make it into the beer. I mean, especially these proteins that aren't, like you said, aren't known to impact beer quality. So I think you might have just answered this question then, but my question was going to be, what are the implications of this research then for brewers?
Well, what we found out so far is that hop will affect the beer quality by changing the protein profile during the wort boiling. Also, the wort protein might be a key to improve the hop bitter acidity's utilization, which is normally low during the wort boiling. So yeah, we are trying to offer some knowledge for not only the breweries, but of course the breweries to improve their utilization during the process.
Yeah, so improving hop utilization, I mean, that would be a big deal, but also understanding the protein breakdown could provide new avenues of research, right? As we understand like which proteins are binding with hops, if we can reduce those proteins, increase our utilization, we might be able to change the protein matrix for other reasons, right? For other things in beer.
Yeah, exactly. We could then open like to have more hazy stability, for example, because some beer styles, the haziness is welcomed, but some are not. Like for a Pilsner, for example, we need a clear beer. And then knowing how these interact, like not only alpha, isoalpha, but also beta acids, this could open a new world to or either improve the haze stability or the foam stability, and then with new hop products.
Yeah. And I mean, again, another question I was going to ask about this too is, I mean, this is my first episode that we've done looking at like proteins this in depth, right? Looking at proteomic analysis, for example. And I was going to ask, how can brewers use proteomic analysis like this to make better beer? Are there other ways that we could use this type of analysis to look at and improve beer?
Actually, thinking about the analysis itself is not an easy one because it's more what we call like fine analysis. So it's quite expensive as well for the breweries, and it's not that accessible, the equipment and the materials. But with the outcome from this analysis, this could really help the breweries to look in deep, as I said, like the barley variety, the profile of protein in the barley or the malt, and also could improve not only the boiling, but also the mashing step by seeing how protein interacts also in the other steps during the brewing process.
Yeah. What proteins are sort of increased or decreased during different processes, like during the malts, during mash, all that stuff. And hop utilization is one piece of the brewing process. And again, this, like you mentioned, this is ultra fine analysis, right? We're looking very specifically at very targeted, very small things. but those changes might have big implications. If you could improve your utilization, or if you can look at your protein matrix and improve haze stability or improve foam stability, those are all ways that this kind of analysis might help brewers make better beer. All right, well, Mariana, we talked about a bunch of stuff today in terms of hop bitter acids and isomerization, and then proteins and coagulation and all this. If you want brewers to take away just one thing from today's episode, what would it be?
Yeah, of course. One takeaway message would be, don't underestimate the power of proteins, because they are everywhere and are really important for the beer quality, but they can also make your beer less bitter. So let's keep this in mind.
Yeah, that's a great one, right? Don't underestimate the power of proteins. I love it. And I look forward to some of your future episodes, right? I look forward to talking with you about how barley variety impacts hop utilization. I mean, I think that's going to be a lot of fun. And then I look also forward to talking about Brazilian hops. I think that's just going to be fun to chat about what hops are available in Brazil and how to make extracts. So, before we do that, is there anything else that you wanted to talk about this study that we didn't get to today?
What I could summarize as well is like our results indicate that enzymes are more likely to interact with hop bitter acids. But also follow-up study is still necessary to really prove which kind of interactions happens between the proteins and the hop bitter acids. And exactly which proteins really interact with which hop bitter acids, because now we had a big picture of what is happening, but one should look in depth.
Yeah. Look much deeper into it to be able to specify, which exact compounds are interacting and that sort of stuff. That'd be another great analysis, and hopefully somebody will look at that in the future. Well, Mariana, thank you so much for joining me in the Brew Lab.
Well, thank you very much, Cade, for inviting me. I am looking forward to talk about my other researches and also the Brazilian hops.
Yeah, me too. All right. Well, listeners, in the show notes, you'll find a link to the article that was published in the Journal of Agricultural and Food Chemistry in March 2023. And next week, Jordan and I will be back applying the science of this episode. See y'all then. The Brew Lab is a production of Brewlosophy, where they who drink beer think beer. Don't forget to visit brewlosophy.com to read about our weekly experiments and other brewing adventures, and listen to us talk about it on our other show, the Brewlosophy Podcast. Thanks to all of our sponsors and patrons that help make this show possible. If you'd like to receive a reward for helping us do what we do, visit patreon.com/brewlosophy to see how you can do just that. Thanks so much for listening. We'll be back in the Brew Lab with another guest next week. Until then, think beer.
Looking for a fun way to win up to 25 times your money this basketball season? Test your skills on Prize Picks, the most exciting way to play daily fantasy sports. Just select 2 or more players, pick more or less on their projected stats, and place your entry. You could turn $10 into $250. Right now, Prize Picks will match your first deposit up to $100. Just visit prizepicks.com/fan and use code FAN. That's code FAN at prizepicks.com/fan.
Must be present in certain states. Visit prizepicks.com for restrictions and details.